In this video, we shall look at a few review problems associated with torque and how it relates to Newton's second law for rotation. First, a brief introduction. Torque is a vector, and it causes rotation. The way to compute torque is as follows. It is a cross product of two vectors. The first vector is called the moment arm vector. The second vector is the force that's producing the torque. So the SI unit for torque is just Newton meter. From the review problems, we will see how to define moment arm in a minute. Since torque produces rotation, it can be expected that torque also produces angular acceleration, and this is the connection between torque and angular acceleration. More specifically, we are dealing here with net torque. The constant of proportionality is the moment of inertia that we have seen in our previous video. This expression is what we call Newton's second law for rotation. Now let's get to the problems. A ball of mass 500 grams is attached to an end of a massless rod pendulum with a length 1.2 meters, as shown. When the pendulum is 26 degrees from the vertical, find the magnitude of torque due to gravity calculated about the pivot of the pendulum. So the pivot is right there, and the pendulum is swinging back and forth about that point. Or I should say about an axis passing through that point, perpendicular to the plane. So let's first calculate the torque. Torque is given by the cross product of two vectors. The first one is moment arm, and the second one is force. In this case, is the weight. So if you want to determine the magnitude of the torque, it is just the same as the magnitude of the moment arm times the magnitude of the force times the sine of the angle between these two vectors. Moment arm is the vector that extends from the support to where the force acts. In this case, the force acts here, where the mass is. And the direction of that moment arm is going from here all the way there. The magnitude of the moment arm is that, which is 1.2 meters. So R is 1.2. The force is the gravitational force acting on that 500 gram object. So the force acts vertically downward. So since it is weight, 500 grams turned into kg is 0.5 kg times gravitational acceleration. Now this g refers to grams, and this g here is 9.81. Now finally theta. Force is vertically downward, moment arm is going like that, so the angle is this angle right there, which is the same as that angle, 26 degrees. So times sine 26 degrees, and that will give you the torque, which will give you 2.58 Newton meter. So that is part A. Let's do part B, the angular acceleration of the ball at that instant. The angular acceleration and torque is related in a following manner. So this is Newton's second law for rotation. Now we know what torque is at that point. We can calculate moment of inertia, and therefore we can determine the angular acceleration. So let's just do that. Moment of inertia for a point particle such as this one is just the mass, which is 0.5 kg, times the distance from the axis of rotation, in this case is 1.2 squared. Substituting this information inside this equation, we can get alpha, the angular acceleration, equals 2.58, is the value we computed from part A, divided by 0.5 times 1.2 squared in the unit of irradiant per second squared. And that's going to give you 3.58 radiant per second squared. And that solves the problem. Problem 2. Figure below shows a uniform disk that rotates about its center. So that is the center, right there. The mass of the disk is 25 grams, radius is 4 cm. It starts to rotate from rest. At t equals to 0 seconds, two forces are applied at the rim tangentially. So that is F, and the other force is 0.12 newtons in the direction shown. At 1.5 seconds, the disk's angular speed is 300 radian per second, counterclockwise. So find the magnitude of F. The direction of rotation is counterclockwise, as represented by this blue arrow. So from our previous discussions in our previous videos, when you have a counterclockwise rotation, the direction of the torque will be out of the board. So in this case, it's represented by this dot. Now let's analyze the directions of torques due to this force and that force. The direction of torque created by 0.12 newtons is as follows. The moment arm is going like that, remember, from the axis of rotation to where the force acts. So that is the moment arm for 0.12 newton force. Now when you use your right hand rule, when you sweep or curl from R to 0.12 newtons, you see the direction of your thumb will be pointing into the board. So the torque created by this force is heading into the plane or into the board. We can take that torque to be negative in sign. Now the torque created by this force, F, the moment arm for that force is going that way. Let's call it R. When you curl your right hand fingers from vector R to F, you see that the direction of your thumb is pointing out of the plane. So the direction of torque created by force F is out of the plane. And let's assume that direction is plus. If this is negative, this has got to be plus. Now let's apply Newton's second law for rotation. Net torque equals moment of inertia times angular acceleration of the wheel. So the net torque is the torque due to this, which is positive in nature, and that's given by force times the moment arm. The magnitude of the moment arm is just the same as the radius of the wheel, 0.04 meter, and that's plus the negative torque, so that's a negative torque. The force is 0.12, and the moment arm is the same as the radius of the wheel, 0.04. Note the angle between the moment arm and that force, the moment arm and this force, is 90 degrees, so sine 90 is 1. So 1 pretty much appears there, so we don't have to explicitly write them out. So this net torque is the left-hand side of this equation. Now the right-hand side. Moment of inertia of a disk is half times its mass. Mass is 25 grams, so you have to change that into kg, so 0.025, times the square of the radius in meter, 0.04 squared. Now what is alpha? Alpha is given by rate of change of angular speed, like that. Or in a non-calculus language, the change in angular speed over the time interval. We know that it starts from rest, and then at some point its angular speed is 300. So that means delta omega is just 300, and it occurs in a time interval of 1.5 seconds right there. So that's your alpha. Equating this entire expression, which is the net torque, to this expression, we can finally solve the unknown, which is the force that we are looking for. And if you do that, you get the following for the unknown force, which is 0.22 newtons. And that solves the problem. Thank you for watching.